The most underrated Nobel Prizes. Number 1. The mRNA vaccine. Katalin Karikó left Hungary for America in 1985 with her husband, her young daughter, and, the story goes, a few $100s sewn into the child's teddy bear, because that was the only way to carry it out. She had one stubborn conviction, that messenger RNA, the molecule that carries instructions around inside our cells, could be used as a kind of programmable medicine. Hand the body a set of instructions and let it build whatever protein you needed. The trouble was that the body hated it. Injected RNA was treated as an invader. It set off a wave of inflammation and was torn apart, which made it look, for years, like a dead end. Grant after grant was turned down, and in the mid-1990s, her own university demoted her. She kept going. With her colleague Drew Weissman, she found the way through. Swap one of the RNA's building blocks for a subtly altered version, and the body's alarm stays quiet, while the cell still reads the instructions and makes the protein. For years, almost nobody noticed. Then a pandemic arrived, and that long-ignored trick became the heart of the Pfizer-BioNTech and Moderna vaccines, delivered in the end in something like 13 billion doses. Studies estimate those vaccines prevented on the order of 15 to 20 million deaths in their first year alone. The laboratory that had once pushed her down a rung had, without quite realizing it, been sitting on one of the most consequential ideas in modern medicine. In 2023, Karikó and Weissman were awarded the Nobel Prize in Physiology or Medicine. Number 2. The malaria drug. By the late 1960s, the old malaria drugs were failing, the parasite had grown resistant, and people were dying in their thousands. Youyou was handed a quietly desperate assignment: lead a secret project to find something new. Her team screened thousands of compounds and got nowhere, so she went back through more than 2,000 recipes from traditional medicine and kept circling one ingredient: sweet wormwood, which kept almost working and then failing. The breakthrough came from a line in a text some 16 centuries old, which said to soak the plant in cold water. Heat, she realized, was destroying the very thing she was after, so she switched to a gentle, low-temperature method, and at last the compound survived. To be sure it was safe, she and her colleagues tried it on themselves first. The drug, Artemisinin, turned out to be one of the most effective antimalarials ever found, and it is credited with saving millions of lives. Together with bed nets and other tools, the global fight against malaria has averted something like 14 million deaths since the year 2000. And the establishment was never quite sure what to do with her. No doctorate, no training abroad, no seat in the academies. The 3-no scientist, as they called her, a little sniffily. In 2015, the Nobel Prize settled the question. Number 3. The blue LED. For decades, engineers could build red light-emitting diodes and green ones, but a bright blue defeated everybody, and without blue you cannot make white, and without white you cannot light a room. The problem was the material, a crystal called gallium nitride that nobody could grow cleanly enough to work, and most of the world's great laboratories had given it up as hopeless. Shuji Nakamura was an unlikely person to crack it, largely self-taught, working at a small chemical company in rural Japan, building much of his own equipment by hand. Carrying on from groundwork laid by Isamu Akasaki and Hiroshi Amano, he found ways to grow and tune those stubborn crystals, and produced a blue bright enough to finish the set. White LED lighting followed, and the world began, slowly, to swap its energy-guzzling bulbs for something that merely sips. In a typical home, going fully LED cuts the lighting bill by roughly 3/4. By the US Department of Energy's reckoning, something like $200 a year, every year, for as long as the lights are on. For rewiring the lighting of civilization, his employer is reported to have given him a bonus of about 20,000 yen, roughly $200. He later took the company to court, and the case was settled for hundreds of millions of yen. In 2014, Nakamura, Akasaki and Amano shared the Nobel Prize in Physics, which paid, one assumes, considerably better than the bonus. Number 4. PCR. To study DNA, you need a great deal of it, but a crime scene, or an ancient bone, or a single cell gives you only a vanishing trace, far too little to read. Copying that trace, quickly and reliably, was the bottleneck that held biology back.
The answer came to Kary Mullis, a surfer, a chemist, and by every account, including his own, a deeply unconventional man, one night in 1983, as he drove up the California coast and pulled over on the hard shoulder. His idea was to run the reaction in cycles, heat the DNA to split it in two, cool it so each half is copied, then repeat, doubling the DNA every round until a single molecule becomes billions. He called it the polymerase chain reaction. It became the photocopier of the genetic age, and almost every advance in modern biology runs through it, catching criminals, reading the genomes of the long dead, and the swab that told you whether or not you had a certain virus billions of times over. We will leave most of the rest of Mullis where it lies, but the idea he had on that dark road was a real turn in the history of science, and in 1993 it brought him the Nobel Prize in Chemistry. Number 5. The Chandrasekhar limit. In 1930, a 19-year-old named Subramanian Chandrasekhar sailed from India to England,
and on the long voyage worked out what happens to a star like our Sun when it runs out of fuel. Below a certain mass, he found, it settles into a dense, quiet ember, a white dwarf. But above that limit, nothing can hold it up, and the star must collapse further still towards stranger fates, neutron stars, and in the heaviest cases, black holes. The hard part was not only the mathematics, which married the new quantum theory to relativity, but who stood against him. The most famous astronomer of the age, Arthur Eddington, thought the whole idea absurd, and said so in person at a major meeting, pulling the young man's work apart in front of the room. It was a wound that took years to heal, and for a while it cost him. But he held his ground. The universe was on his side, and one by one the rest of physics came round. He had helped reveal the path that leads from dying stars to neutron stars and black holes, decades before anyone could observe either. The Nobel arrived in 1983, a little over half a century after that voyage. Eddington never publicly recanted. The cosmos, mercifully, did not require his sign-off. Number 6. The lithium-ion battery. The battery in your phone, your laptop, and very probably your next car traces back to a chain of 3 people, and to one in particular, John Goodenough, who came late to physics and won his Nobel later still. The obstacle was a nasty one. Lithium can store a great deal of energy, but the early lithium batteries had an alarming habit of catching fire. Stanley Whittingham opened the door with the first design. Around 1980, Goodenough found a cathode material that roughly doubled the voltage, and Akira Yoshino then engineered a cell that was both safe and practical to make. Between them, they made the portable, rechargeable world possible. The batteries now sit inside billions of devices, and increasingly inside the cars on the road. Goodenough shared the prize in 2019 at the age of 97, the oldest person ever to receive a Nobel, and was, by every account, still going into the office. He kept at the research almost to the end of his long life, and the 3 of them had quietly charged up the modern age. Number 7. X-ray crystallography. To understand a molecule, to make a drug from it, you need its exact shape, the position of every atom. But molecules are far too small to see, and you cannot simply photograph an atom. Dorothy Hodgkin's method was to fire X-rays at a crystal and read the pattern of scattered shadows, then reconstruct the architecture within, painstakingly by hand, long before computers could help. She mapped the structure of penicillin, then the fiendishly complicated vitamin B12, and later insulin. And that knowledge of exact shape is what lets chemists design drugs that fit their targets, the foundation of a great deal of modern medicine. She did much of it with hands increasingly knotted by rheumatoid arthritis, diagnosed when she was still a young woman. And she remains to this day the only British woman ever to win a Nobel Prize in the sciences. When she won it in 1964, at least one British newspaper decided the most important thing to report was that an Oxford housewife had done rather well. Number 8. Chemical neurotransmission. When a nerve tells a muscle what to do, how does the message cross the gap? Does it leap across as electricity, or does it pass a chemical note? Nobody knew, and nobody could see how to test it. The events were too fast and too small to catch. The answer came to Otto Loewi in 1921 in a dream. He woke, scrawled it on a scrap of paper, and went back to sleep. And in the morning, found the most important sentence in neuroscience reduced to an unreadable squiggle. Mercifully, the dream returned the next night, and this time he went straight to the lab. The experiment was elegant. Stimulate one frog's heart, take the fluid around it, drip that fluid onto a second heart. And the second heart slowed too, proving a chemical had carried the message. We should take the dream itself with a pinch of salt, since it is his own much-polished story. But the chemistry was solid. It founded the study of the brain's chemical signals, the very signals that nearly every drug for depression, pain, or Parkinson's acts upon today. And it won him a share of the Nobel Prize. Number 9. The digital camera sensor. For over a century, capturing an image meant film, chemical, analog, and slow. The unsolved problem was how to catch a picture electronically, how to turn light into a grid of numbers a machine could read. In 1969, at Bell Labs, Willard Boyle and George Smith sketched the answer on a blackboard in a little under an hour. Their charge-coupled device was a grid of tiny wells that catch light, count it, and pass the tally along like a line of people handing buckets down a chain. It became the eye of the first digital cameras and of the Hubble Space Telescope, and it laid the foundations for the image sensors used in phones today. Film, after more than 100 years, was quietly shown the door. When the Nobel came in 2009, Boyle and Smith split it with the inventor of fiber optics. They had always, it seems, been good at sharing. Number 10. The integrated circuit. By the late 1950s, electronics had hit a wall engineers called the tyranny of numbers. Every added function meant more separate components, each wired to the next by hand, until the sheer tangle of connections capped how complex a machine could be. In the summer of 1958, Jack Kilby was the new man at Texas Instruments, too junior to have earned any holiday. So while everyone else went to the beach, he sat in an empty lab and thought. His idea was to stop wiring components together at all, and instead carve the whole circuit, parts and connections alike, out of a single sliver of semiconductor. By September, he had built the first working one. Robert Noyce arrived at much the same idea independently and built a more practical version, and the two are rightly remembered together, though Noyce had died by the time the Nobel came, and it cannot be given to the departed. Every computer and every phone descends from that lonely summer, and the chips themselves are now made by the billions every year. The prize went to Kilby in the year 2000, 42 years after the holiday he never took. Like and subscribe if you want more videos like these, and every name, date and claim in this video is set out with its sources in the description below, along with a few places to go if you'd like to learn more.